branch prediction buffer. So up to now, we have seen the branch prediction by using one bit branch prediction and 2-bit saturating counter branch prediction part. Okay, saturating counter. Okay, so now we have seen that in 2-bit saturating point, and in that case, in some programs, we may find many branches, right? We may find many branches. So then how to handle them, how to maintain their history, like we used in the in the 2-bit saturating, right? So to do that, we just consider into the branch prediction buffer, or we called it as your branch history table, BHT. So in branch history table in 2-bit saturating, what we have done. First, suppose if you have the branch one in 2-bit saturating, counter for branch 1, there is a buffer is used, small buffer unit is used, which is, we call this as your 2-bit saturating, the buffer. So that holds like, the branch states like 0, 0, 0, 1, or we can say that, branch is taken, branch is not taken, that prediction will be taken. So suppose for branch 1, this will be there. Suppose we have another branch, branch 2, that will also have a branch, what you call the 2-bit saturating counter buffer, like 0, 0. If you have another branch, suppose branch 3, that will also hold the status of the branch, whether it will be taken or not. So like that, if we have some n number of branches, suppose we have some n number of branches. So for all those n number of branches holds this, the 2-bit saturating point. So how to handle all these n number of branches means then we are going to take for this branch prediction buffer, consider it takes one array. In that array, all these entries will be, for every branch, there will be one entry in that array. Okay, and that array is your 2-dimensional array that holds 2 bits. Because we are taking the 2-bit saturating, so that holds 2 bits. So those 2 bits will be again stored in this, like for branch 1 0 0, branch 2 0 0, branch 3 3 0, or something like that. The 1 0 or 1 1, something like that. The branches will be given in this case, stored in this case. So now, how to identify these branches then? How to identify these branches? So this branch, it is an array. It is an array of 2-bit saturating counter. So it is a small memory space. So it will be identified with the address. Okay, every branch will be identified with the address. Okay, so some address will be given 1000 or 1004, 1008, and so and so it continues. Correct? But we know that this is a small, we are calling it as a buffer, a small piece of memory. So, how much it can take, or there is a limited number of buffers in the CPU, central processing unit. So it takes in this buffer, by combining all these together as an array, we call this as your branch history table. In this branch history table, it takes at most 2 to the power of k entries will be there. 2 to the power of k entries will be there. Okay. So in this 2 to the power of k entries means in theory, it takes 2 to the power of k branches. It can accommodate 2 to the power of k branches. But in practicality, because of this limited number of buffers, it takes, the very limited number of memory will be reserved as buffer to store these branches. Then how to identify these branches means, the branch, for every branch we know that in the program counter holds the address of your branch. Program counter holds the address of your branch, So in that, what is the size of this program counter? Size of program counter is your 32-bit. 32-bit. In 32 bits, the address representation of your branch. Okay. So then, it starts from your 0, then 1, 2, and it ends with your 31-bit. So to give the address, to identify these branches in the branch history table, the lower 13 bits, the lower, 12 bits, lower 12 bits of your program counter will be taken, and this lower 12 bits, the lower 12 bits of your program counter will be given as an input to a hash function, That hash function generates the identical value, so that we call the entry number, or entry, that value is entry number. So based on that entry number, or we call this as your address, based on that address, whether this branch and whatever content is there in that address, that gives the whether that branch is taken or not. If the entry is 00 means strongly not taken. If the entry is 01 means, if 00 means strongly not taken. If 01 means it is likely not taken, that we have observed in the 2-bit saturating counter state diagram. If it is 11 means strongly taken. If it is 10 means likely taken. So those status will be there in this branch history. The content of this branch history table defines whether that branch is taken, strongly not taken, or likely not taken, or strongly taken, or likely taken. So once, to get this status, we need the address. So that address comes from the program counter, lower 12 bits. That lower 12 bits will be given as an input to your hash function. From that hash function, it generates a digest, or we call the value. That value gives the address of this branch history table. So that we call that address mapping, whether the branch is taken or not. So this is, in practice, it is very limited. In this case, it is taken 12 bits. So there will be 2 to the power of, when k is equal to 12, then there will be a 2 to the power of 12 entries will be there. 2 to the power of 12 entries will be there. So it is to the power of 12, it may give you 4096 entries will be there. 4096 entries will be there. So from the program counter, it holds the branch address. In this branch address, the lower 12 bits will be taken, and that goes through your hash function that gives the value of your address, which are in this buffer address, to identify what is, where the branch status is there in branch history table. Okay, so now let me tell you, suppose in some cases, if lower 4 bits are taken, then how many number of entries will be there in the branch history from program counter? If lower 4 bits are taken to map the address of your branches table, then what is the number of entries? Good. Okay. If it is 8 bits, suppose. Good. Correct. That's right. Yeah. So this is how, now how many branches are there in our program and how they can be accommodated in branch history table. So this is the case of maintaining branch history table. Now, you just recall that for this branch prediction, we need to perform two operations, right? We need to perform two operations. One, first we are going with the whether the branch will be taken or not taken. That we call branch prediction in the branch, in the control hazard. Second, what we need to do in the control hazard, we are going to calculate the branch target address, right? Branch target address. Whether the branch is taken or not, we are going to calculate the branch target address. Okay. So before going to talk about this branch target address, so this is the general way of representation of your branch history table. So as said, the branch history table is a small memory which is indexed with the lower bits of your branch instructions address. Where this branch instruction address will be there, the branch instruction address will be from your program counter. Right? So why the low bits means, why this low bits means the branches sharing the same lower bits that share the branch history table entry, thus gives some interferences. That gives some interference. That means the same, the memory location can be the same memory location can be used by some multiple branches like branch 1, your branch 2. Okay, so that's there is a possibility of two branches which can occupy the same. So to come out of this one, then the lower bits will be used to identify their exact location. But actual implementation of this branch history table is this the 2-bit saturating a 2-bit attached to each of these blocks. So this branch history table implemented within the instruction cache memory only, within the instruction cache memory only. Okay. So in that instruction cache memory, where do you find this instruction cache memory? The general instruction cache memory we found in two different stages, right? Okay. Without dividing the instruction memory, without dividing the instruction cache memory, where do we find, in which stages of your pipeline we find this instruction cache memory? Can you please give the answer in the chat box? In which stage we find this instruction cache memory? Thomas, good. Benjamin, good. Okay. Okay. Correct. Yeah. So now the question is, if the instruction memory is not separated, then if the instruction memory is not hardwarely separated, then in which stages we find this instruction memory? Thomas, super, good. Yeah. That's great. Okay, so the implementation of the branch history table, where this instruction memory, we divided into, to solve the structural hazard. We divided this into, one is your L1 cache. We are going to talk about these caches. L1 cache, okay, which holds we treat as your instruction cache, and another L1 cache, which is for your L1 cache is there, that is for your data cache, instruction cache and data cache. So as most of you have given the very right answer, so instruction cache will be at the instruction fetching stage only. So in this instruction fetching stage, that requires a separate memory which is accessed during this instruction phase to implement this. From that instruction cache, we use another small buffer to implement this branch history table. So the caveats here is it cannot separately size that I cache and your branch instruction. They together only. They together only, right? So then as said in this instruction, it takes last lower 12 bits and then it generates 4096 entries. In that entries, whatever the values are there, 01, 00 or 11, that gives whether that branch is taken or not taken. So mean to say that branch history table is a buffer that exists in the instruction cache memory only, and that instruction cache memory accessed at the instruction fetching stage. This buffer, branch history table holds the entries of 2-bit saturating counter entries will be there. That says whether the branch is strongly taken, whether the branch is taken or not taken. So beside the branch prediction, as said in the control hazard, beside the branch prediction, there is one more, the operation needs to perform, that is your branch target prediction. Branch target prediction. So beside this predicting the branch, whether the branch is taken or not, we need to calculate we need to find the effective address, or we call the branch target prediction. So the branch target prediction, that also needs to be predicted whether the same address will be accessed, target address, or different target address will be accessed. So for that, another buffer will be invented. We call that as your branch target buffer. Branch target buffer. Branch history, buffer is different. The branch history table. Another one is branch target buffer. So this branch target buffer is to store the storage used to store the branch target addresses from the previous execution of the branch. Previous execution of the branch. Right? So this is essentially a cached design, and if the predicted branch is taken, so if the predicted branch is taken, the cached target address which is stored in this branch is extracted as predicted branch target. Extracted as predicted branch target. So this branch target buffer is also similar to your, the branch prediction one, but here it uses an array. Here it uses an array. Okay, that array holds the address of your branch. Branch address will be there in this case. So in this there is one array. That array we call this as your branch target buffer. This branch target buffer holds the entries for the branch address. Branch address. It holds the branch address values. Okay, and which is similar to your branch prediction, branch history table, which is similar to your branch history table. So how to identify whether the same address will be retrieved from this branch target buffer or different means? It must be mapping from your instruction branch instruction only, from branch instruction address only. So where this branch instruction address will be stored, this branch instruction address will be stored in the program counter. From that program counter, again take the lower 12 bits and apply to the hash function given as an input to hash function. Okay, so here this line gives that the series of 12 bits are taken from 0 to your the 11, and that will be given as an input to your hash function, and whatever value comes, the outcome comes from this buffer. So that will give the entry of this array, and from there it will check whether this branch which is taken previously calculated the target one, it can predict the branch target address, whether the same address will be taken or different address will be taken. Okay, So then, this is the branch history table and the branch target table. So by using this branch history table and branch target table, okay, the buffer, now how these advanced branch predictions will be taken place. So in this advanced branch, the advanced branch prediction, up to now, whatever we have discussed in previous examples, let me take you to this. We have considered for 2-bit saturating that we have taken the for loops. We have taken the for loops. Okay. We have taken in this, for loop, what we have taken first, we initialized the variables in this for loop, and then we started executing and we found what is the branch outcome is there. From there, the hardware prediction that we have done by using your 2-bit saturating status. Okay, so this maintained the state that maintains that the branch prediction, or we call the branch history table, maintain this status. Okay, so then comes to in advanced branch prediction, it takes other than the loops, other than the for loop or do while loop, if some other loops are there, which we call them as your correlated branches, That means what? The outcome of your previous branches, will give the prediction of your next branch. So let us consider this. We call them as your correlated branches, and let us consider C code here. Example here. If A is equal to 1, then this branch will be taken, and 2 is assigned to C variable. Okay. If B is equal to 1, then 2 is assigned to a variable D. If so, in C is equal to 2, then 2 will be assigned to a variable E. So let us assume that if the first branch is taken, if A is equal to 1, if it is true, it will be taken. And if B is equal to 1, if this branch is also taken, then it indicates that from these two, it indicates that C will be 2 and your D will be 2. Okay. So further, it indicates that C is equal to 2 and D is equal to 2 means C equal to 2. So further it indicates the third branch. If I give the branch instruction 1, branch 2, and branch 3, then it further indicates that the third branch will be taken. The third branch is also taken. The third branch is also taken. So from this example, you can see this. The third branch, whether it is going to be taken or not taken, this depends upon its previous 2 branches. It depends upon previous 2 branches. So we say that whether it will be taken or not taken, that is correlated to previous 2 branches. So then we call that these branches are correlated branches. So the if statements here. So as said, there are 2 branches are taken. Okay. So now suppose there are some cases that if therefore if I have a branch called I have one if branch that depends upon the previous m branches. That depends upon the previous m branches. Suppose m branches. That means what? Your first if branch, second if branch, third if branch. So like that, it is the M branch, if M branch, okay. So then, the M plus one branch, that depends upon the prediction of, that depends upon the results of or outcomes of this, whether this branch will be taken or not, that depends upon the prediction of, the prediction outcome of these branches. This branch out depends upon these branch outcomes. If these branch outcomes are taken, then it will be taken. If not taken, then it will not be taken. So we call this as your M branch to predict the M plus one branch, whether that branch will be taken or not taken, will be taken or not taken. Okay. So in this concept now, for every branch, there is a status whether it is taken or not taken. Okay. Whether it is taken or not taken. Okay. So to maintain this for every branch, what we are going to do, we are going to maintain a 2-bit, we are going to maintain a 2-bit saturating saturating counter. 2-bit saturating counter. Okay. In this 2-bit saturating counter, it will maintain whether the branch is taken or not taken, whether the branch is taken or not taken. Okay. So this procedure, by maintaining an array, and in that array, by taking one register and storing these values, whether these previous M branches, whether these previous M branches are taken or not taken for the prediction of your employees on one branch, we call that as your, for that, the implementation requires the global branch history register. Global branch history register. Okay. So now this is what we just discussed, correlating the branch prediction. Okay. So in this correlating branch prediction, the predictor predicts if a branch instruction is taken or not based on the outcome of previous M branch instructions. Previous M branch instructions. Okay. So in our previous example, there are 3 branches. Okay. The third branch should be predicted that taken if the previous 2 branches are taken. So to maintain this M branch previous M branch history, we need the history register. We call the global branch history register. We call global branch history register. So in this global branch history register, what it says with M-bit global branch means if there are M branches are there, if there are M branches are there, then there is one global branch history table. Then there one register will be maintained. In that register, okay, it is a M-bit register. It is a M-bit register. So there will be M bits will be there in this register. This M bit register, it indicates whether the branch, previous M branches status will be there, whether they are taken or not taken. If they are taken, then the entry will be 1. If not taken, entry will be 0. If they are taken, entry will be 1. If not taken, entry will be 0. And this 0, 0, for example, this will be maintained. So there will be M bits will be there. The size of this one is M bit. M bits. In this M bit, it starts with the 0th bit, and ends with your M minus 1 bits. Okay, and in the entry in every bit position is only there is a 1 bit entry is there. So this bit says whether if it is taken, then the entry will be 1. If not taken, the entry will be 0. If the branch is taken, entry will be 1. If the branch is not taken, entry will be 0. Okay. And similarly, suppose if it is the ith bit, this ith bit indicates or records, ith bit record the history of record the history of the ith branch, whether it is taken or not taken. Whether it is taken or not taken. In this example, if the entry at this ith bit is 0, then what it says is that branch is taken or not taken. Please answer in the chat box. If the ith bit entry is 0 in mbit register, global bit history table, then the branch is taken or not taken. Good. Yeah. If it is 1, then correct. Thank you. Thank you. If it is 1, then taken. Correct. Correct. Okay. 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 Thank you. So that's the entry of this one. So now let me consider, let us take one example. Then how to maintain the entries in this, mbit global branch history register. So from our previous example, let us just take that we are using 2 bits. Suppose m is equal to 2, okay, by following m is equal to 2 means the size of, if m is equal to 2, then size of your global history, global branch history register have 2 entries. It have 2 entries, right? Because m is equal to 2. If m is equal to 5 means there will be 5 entries will be there. Okay. Now let us see if I have the branch. I have one branch 1. Okay. Branch 1, branch 2, if 2, and branch 3, if. Now here the question is, I have m is equal to 2. M is equal to 2. So what it means, m is equal to 2 means how many branches it will take to predict the next branch. If m is equal to 2, how many previous branches it will take to predict the next branch? Are you getting my question? If m is equal to 2, how many previous branches it will take to predict next branch? Somebody says 1, somebody 2, somebody 4, somebody 4. No. I'll just write the question. If, the global branch history table is supposed to be, if m is equal to 2, then how many previous branch outcomes it takes to predict next branch, whether it will be taken or not taken. From our previous example, if you see, if m is equal to 2 means previous 2 branches previous two branches, branch 1, branch 2 will be taken. Based on this, if they are taken or not taken, based on this, it is going to predict whether the third branch will be taken or not. In the similar way, if m is equal to 5, if m is equal to 5 in global branch history register, then what it means? Stick with 2. Yeah. If m is equal to 5, then how many previous branches or previous branch history it takes to predict next? Very good. Yeah. So it must be clear that in the branch history, we are talking about global branch history register, not branch history table. In branch history table means it takes status. Okay. Correct. Yeah. Correct, Thomas. Okay. So from here, don't be confused that you are taking m is equal to 5 bit means 5 previous branches will be taken to predict the sixth one. To predict the sixth one. So how it will be implemented then? How it will be implemented on branch? So global branch, the history register. Here we are considering m is equal to 2. That means the previous two branch history will be taken to predict the next one. Okay. So let us consider that I have the one branch, if branch, and second branch, if, okay, and the third branch, if. So in m is equal to 2 means previous two branches will be taken. If the first branch, suppose if it is taken, and second branch if it is not taken, then what will be the entry? What will be the entry in this table? What will be the entry in this table? Branch, global branch history register. It is 10, correct. First one is taken, second one is not taken. So from here, the entry, the first bit will be, holding the entry of your first branch, second bit holding the entry of your second branch. So the entry here is 10, 10. Okay. So based on this value, okay, the third branch, whether this branch will be going to take or not taken, that we call the branch prediction. Okay, the outcome of the previous two branch. Okay, the outcomes of your previous branch, branch history, previous branch history. It predicts whether this branch will be taken or not taken. Or not taken. Okay. So now suppose if I have the fourth branch, to check whether the fourth branch will be, to predict whether this branch will be taken or not taken, in that case, which previous branch history will be taken? To predict whether branch 4 will be taken or not taken, which previous history will be used? Is it 1, 2 or 2, 3 or 1, 3? 2, 3. Yes. Previous sequence of previous branch history will be taken. It is 2, 3. Okay. Good. So the 2, 3 will be used to predict whether the fourth branch will be taken or not taken. Okay. And this process, because if we are taking only m is equal to 2 means previous two branches will be taken. If there is a fifth branch, suppose, then for fifth branch prediction whether it will be taken or not means that will consider previous two sequence of two branches 3 and 4. Okay. So that is one thing. So then how this entry will be updated in the global branch history register? Global branch history register. Okay. That means suppose first one is taken, second one is not taken. Okay, if it is from this outcome, if it says likely taken, 10 means it will be in likely taken state. So your third branch is taken now. When third branch is taken, its status must be, its history must be updated in this branch history table. It must be updated in the branch history table. So then how it will be done? How it will be done? So in this case, how it will be done means it takes the left shift operation. Left shift operation in the array, the left shift operation will be there. Okay, that means to predict the previous two are taken and this 1 and 2 are taken and their history is taken and third one is updated. So for future prediction, one is not required. Okay, so it's this bit will be shifted, that will be removed from your branch history register. So this 0 move to this location and your third one is taken, so 1 becomes here. Now this history is used to predict the fourth one. If it is also suppose taken from this, if it is also taken, this status says that likely not taken, but prediction gives, assume that prediction outcome comes, suppose taken, example, assume that. Then what happens to predict fifth one? Once it is taken, then this will be updated as by doing the left shift operation. Left shift operation. Here, this one move to this position, and if it is also taken, then that one comes into this one. So this is the way of implementing the mbit global branch history table. Mbit global branch history table. Okay. So what to remember? If 2-bit means only previous two instructions will be considered. Their history will be considered from this register, whether they are taken or not taken. Second, once the prediction done, then the global branch history register will be updated by performing the left shift operation. Left shift operation. Left shift operation. Okay, to maintain the accurate data in this global branch history register. Okay. So that is a typical mbit correlating the global branch history register, that GBHR we said, that stores the outcomes of m branches. M branches. Here we took m is equal to 2, so it takes 2 branches right before the branch to be predicted. Then a mbit shift register is used to record the outcomes of m previous branches. M previous branches. So this is what we have just observed in the example. So this shift operation will be done, left shift will be done. So then, in some cases, if there are multiple, branches are there, and we need to give an accurate result for the branch prediction, for correlating branch prediction, then it is the voice to take that m comma n correlating branch prediction. So this m says the how many branches will be taken to predict the next, or the how many branches will be taken to predict the next branch that will be taken or not. So we can say that this mbit history says that the previous branches. Second one is by applying the 2-bit or 3-bit or 4-bit saturating counters to this, it will give an accurate correlating branch predictor is possible. So we write that as m previous branches are taken to predict the next one, and to check whether those branches are taken or not taken. To maintain that, use the 2-bit in our previous example which we are considering, use the 2-bit saturating counter, 2-bit saturating counters. by combining these two, how we are going to design it. How we are going to design it. So if there is a m-bit history is there, means how many there will be. M-bit means m branches will be there, right? M-bit means m branches will be there. For every branch, there will be a branch history table. For every branch, there will be a branch history table. That branch history table maintains whether the branch is taken or not taken. Whether the branch is taken or not taken. Okay. So for m branches means m, how many branch history table will be generated means that gives how many bits taken or not taken. It makes two stages. So 2 to the power of m branch history table, 2 to the power of m branch history tables will be. Okay. So that means suppose if I have the m bit register, m bit, your global branch history register, which holds the m bits, starts with your the zeroth bit, 1, and so it goes with your m minus 1th branch, m minus 1th branch. In that, it will maintain if it is taken, then 1, if it is not taken, then 0 will be there. So for every branch, there is a branch history. For every branch, there is a branch history table. Branch history table. For 0th element here, for 0th branch, okay, the 0th branch table will be there. The entry in this branch history table, is a 2-bit saturating, because we in our example we are saying that n is equal to 2, because up to now we consider 2-bit saturating counter. So there will be 2 bits will be there. Okay. So likewise there are m branches are there. So for every branch there will be a branch history. There will be a branch history table. The branch history table of your m minus 1, this, for suppose the ith branch it is, the ith branch, then ith branch table, branch history table for ith one. So similarly, these, for every entry there will be a branch history table one is there. So this way in the m comma n correlating branch predictor, there will be m branches. For every branch there will be branch history table. That branch history table maintains whether the branch will be taken, strongly taken or lightly taken. That status will be there, right? So in this branch again, whether that branch will be taken or not. Okay. So how to maintain that? So it requires a this m branch register. From here it identifies which branch will be taken. In that branch, after the branch is selected, then as usual the branch will be mapped with the addresses. So that address will be, how those addresses will be there in the program counter. In the program counter, the branch address will be there. From that branch, the lower 12 bits will be taken. Those lower 12 bits will be used to identify the branch location in that branch history table, and in that location it gives the information whether the branch is taken or not taken. Okay. So this is same as your the branch history table in 2-bit saturating counter. So this we call this as that the example for this prediction is if there are n branches are there. In our example we are taking m is equal to 2 and n is equal to 2. So how many branch history tables it requires? If M is equal to 2 means how many branch history tables it requires? Perfect. So 2 to the power of 2. That will give 4. Correct. Good answer. Yeah. So M is equal to 2 means the branch history table is equal to 2 to the power of M, that is equal to 2 to the power of 2 equal to 4 history tables will be there. So those for which table should be taken or not, that should be maintained by your branch history table. So this is your global branch history register which finds the branch history. Okay, in that branch history here it is 10 means it will generate to the power of 4 tables. So consider the branch history table 0, branch history table 1, branch history table 2, and suppose branch history table 3 is there. Branch history table 3 is there. So in this case, if the entry in the branch global branch history register is 10, that means the 10 of your binary form that gives your 2 of your decimal form. So it is going to select the which branch? It is going to select branch 2. Branch 2. Once this the branch history table 2 is selected, after that, as usual, what happens in that branch history table where that branch is located, where that branch is located, okay, to check it out, to locate that branch, the address should be mapped from that branch history, the branch address which is there in the program counter, take the lower 12 bits, that will give the location of your branch in this branch history table. In that location, once it is identified the location from here, once it is identified, first it comes from here, then it identify the location of the branch. Once location is identified, from that entry, whether it is taken or not taken, that will be decided. So this we call the M cross N, M cross N, or MN correlating branch predictor, MN correlated branch predictor. Okay. So then the combination by joining the branch history table and correlated one, there is another predictor we call advanced method we call the tournament predictor. In tournament predictor, it combines normal branch predictions as well as correlated branch predictions. So in real programs, actually what happens in real program, some branches are related to other branches. That means it is, it takes the advantage of this method, which one correlated. Correlated prediction is better for this, some branches which are related to other branches. So uh, the correlated prediction is better for this, better. And some branches are independent branches. Some branches are independent, like your for loops and those things. So for these kind of things, it requires 2-bit saturating is enough. 2-bit saturating counter prediction is good for this one. Better for this one. 2-bit saturating counter is better. So in tournament prediction, what it does, therefore, sometimes this correlating predictor is better and sometimes this simple predictor is better, 2-bit saturating. Then in tournament branch prediction, it combines both of these two. It combines both predictor and dynamically choose the best one. Dynamically choose the best one. So when it dynamically choose the best one, then that will give a good performance of your, the computer architecture. So it gives the local pre-branch prediction, which is accessed by your program counter, local pre-branch prediction, which is accessed by your the program counter is your independent one. For correlating predictions, that is based on the last m branches, which are accessed by the global history. So the indicator of which had been the best predictor for this branch means it is if the branches are suppose the static, I mean what you call the simple branches, like independent branches, then this tournament works for that one also by going through the 2-bit saturating counter. If the branches are depending on the previous related branches, then it can go with the correlated branches. So both are combined together. Both are combined together to increase the performance of your the architecture. So 2-bit counters increase for 2-bit counters increase the performance for your simple predictors and decrease the performance for correlating one. So in that case, for correlating one, instead of taking only 2-bit, it can combine with the history also. So that will improve the performance, accurate performance. A branch prediction will be given. Accurate branch prediction will be given. Okay. So with this tournament predictor, I would like to stop the session. In the next class, we'll try to discuss the other speculative predictive mechanism, the execution mechanism, that is memory disambiguation, that we'll discuss in the next class. With this, I would like to